Good morning. Today is March 13, 2020. It is a Friday, and just last night, the president, through a press con, uh, announced the extension of the class suspension to April 12, 2020. This means that we will not be able to have classes in UP Diliman. Therefore, all of our resources, all lectures, will be converted into an online format. So what do I mean by the online conversion? No? All our problem solving sessions will be converted into videos. No? Instead of having uh, lectures in class, all problems and what do you call this, lectures will be delivered through YouTube. No, I already set up a channel in which I will um, give you my lectures, no? And you will be updated through text if they are already available. No, this is for people who are who do not currently have stable access to the internet. No? So regarding problem sets, I will not be very strict about the deadlines, no, because the utmost priority right now is your safety. Uh, for those who are not, or for those who do not have a stable connection to the internet, the deadlines will be a little bit flexible, no. Um, I already listed down the names of those who texted me about their current situation. Rest assured that I will be um, considerate, no, in your case. You do not have to worry about it. Okay. So what we do is to evaluate the magnetic field due to a circular current loop. The previous lecture was on the application of the Biot-Savart law in obtaining the magnetic field due to a straight line wire, a current carrying wire that is just a straight line. That is fairly easy because it's simple. It's just a line, so the integration is pretty straightforward. However, in the case of a circular current wire, um, the approach might not be that obvious, no? So that's what we'll be dealing with in this lecture, no? The objective for the first part of this lecture is, of course, to find the magnetic field vector anywhere in space due to a circular current loop. And that, of course, we will do using your Biot-Savart law. So, using the setup wherein there is a here you have here a loop, no? A circular loop of radius r that is located, or well, that lies on the xy plane. So you can imagine the vertical case, no? We can place your loop here flat, no? And we are considering some point P, a distance z along the z-axis, no? So if this illustration is quite what do you call this, complicated to imagine, you can imagine a loop that is horizontally placed, no, and consider a point from its center, a distance z along the axis, pinching through its center, no? So we ask, what is the magnetic field at point P? In this problem, point P is actually located here, no? Your point P, or the field point, is located here, and that field point is some z distance, no, from the center of your circular loop, no? Again, the important elements in this derivation is of course your DL, which is the infinitesimal length vector, and your R hat, which is your unit vector. Always remember that this unit vector is defined in terms of your what do you call this? Your position vector. So, for example, this is the vector that I was referring to. We can think of this vector as the um, the position, no, of point P with respect to an origin that is located at the source. No? So here, our hat is defined as, R vector is defined as some R, which is the magnitude of that vector, multiplied by the unit vector, R hat, which defines the direction of your R. Of course, this R hat is just this R is just a vector that is pointing from your source point, no, towards your field point. So always remember that when setting up the problem. No? Um, so if we are able to obtain what DL is and what DL is and what R hat is, much of all the calculations will be pretty straightforward. No? Of course, the working expression for this is your infinitesimal BO-Savart law. No? So, alam natin to. We know what DL is. We know what R hat is. We know R squared to be the square of the magnitude of this vector, or the R vector. No? And this is just some 10 times, 10 to the negative 7 factor. No? So, how do we obtain your magnetic field for this particular length vector? Huh? Now, we know that dl cross r hat is just, it is, we know that dl cross r hat is just your dl sine phi, no? Where phi is the angle between dl and r hat, no? Now, if we try to translate, so for example, you know that dl is a vector, no, here, and translate this vector towards this point, you will see that dl is actually pointing that way. So this is your dl. And we can actually do a geometric argument, but it's not very easy to set up a drawing for this, but you can imagine that dl and r hat actually are perpendicular. So this is a right angle here between dl and r hat. So whatever sine phi actually is just equal to 1, since your phi is just equal to 90. No? Now, you might notice that there is a mention of an infinitesimal magnetic field vector component along the z direction. Now, there is a reason why we are only interested in the z component, which is this one. No? And we can actually argue, no, that components along z are the only components that will survive the integration. No? First, what we have to do is to draw, no, a projection. No? Let us try to draw a projection. Oops. Let us draw a projection of this axis. So imagine that this is your y-axis and this is your z-axis, such that the ring is somewhere here. So let me draw that in a better way, a better manner. So this is your z. So you have here your ring. No? So um, if this is your ring and this is your y and z, no, we are sure that DL in this point of the ring is pointing out of the page. So I will denote that using the usual notation. No? While DL somewhere here, which is opposite, so the observation points are the source points are this one. So let's call this DL1, and another that is opposite to that DL1. Let's call that DL2. Here, this is DL1 and the other is DL2. Okay? Now, it is easy to show that this DL1, DL2 is pointing. If you look from this perspective, it's pointing to the into the page. No? So here, this is your negative x. This is your positive x. Okay? So, ganyan lang siya. Okay? Now, let me erase this first. Now that now that we know the direction of DL1 and DL2, what we have to know now, for now, is to identify what R hat 1 and R hat 2 is. No? So at point P, no, we can actually draw a broken line, no, that connects the observation points, the observation point P, no, or the field point P, and the source points 1 and 2. No? Due to 1, no, R hat is pointing in that direction. No? It's just in the same line connecting your what do you call this? Your source point and field point. So this is your R hat 1. No? On the other hand, if you try to construct a vector from source to point P, what you get is an R hat 2 that is pointing in this direction. So okay, so we already identified what R2 is, what R1 is, DL1 is, and DL2 is. So we already know all the directions, no? So we can actually analyze, no, what DL1 cross R1 cross R hat 1 is, and what DL2 cross R hat 2 is. No? For the first one, which is DL1 cross R hat 1, let me draw that using green color. So DL1 cross R hat 1, so this one, so this is your DL1, your R hat 1 is pointing in that direction. No? This tells us that your what do you call this? Your magnetic field via right hand rule is pointing in this direction. So this is your R hat 1, this is your DL1, this is your DB1 direction. No? So this is your DL1, R hat 1. No? On the other hand, let me draw DL2 cross R hat 2 using the blue color. No? So for DL2 cross R hat 2, you have here a current that is flowing into the page, no? and R2 that is pointing in that direction. So this is your R hat 2 and this is your DL2. No, DL2 R hat 2. No? Now, if you do your right hand rule for DL2 R hat 2, so again, so I was not able to illustrate it before, no, for DL1 cross R hat 1, but let's do your right hand rule for DL2 cross R hat 2. So DL2 cross R hat 2. So actually, the magnetic field, so let me erase this first. The magnetic field is pointing in this direction. So this is your DB2, no? And this is your DL2. Okay. Okay. Now, combining, diba, vectors can always be um, added using your superposition. Just add the components of dB1 and dB2 along your orthogonal basis, or your, for example, in this one, it's y and z. You can take the components of dB1 and dB2 along y and z and see how their components add up or cancel out. No? Now, um, let us erase this first, your r hats. No? Now, based on our analysis, we can see that your dB1, no, is pointing in this direction. This is your dB1, while your dB2 is pointing in this direction. Okay. Now, can easily see, no, since there, here's one more thing that you should take note. No, this angle theta is equal to this angle theta. No, so also the what do you call this? The distance of DL1 to the point P and DL2 to the point P are the same. No, they have the same orientation and they have the same distance. No, hence we are pretty sure that the components, no, of dB1 and dB2 along by and bz have the same magnitude. No, but first let us look at how this plays out. No, uh, here dB1 can be decomposed along the y direction and the z direction. So there is some let me write that down. So you have a d b1 y, sorry, let me erase that. So you have here a db1y and a db1d, oh shit, sorry, you have here a db1z, where db1y and db1z are the components of the vector db1 along the y and z direction. And on the other hand, you have a db2, so db2y and a db2z, no, along their respective db2z, no, along their respective axes. No? Now, we can easily see here that this component exactly cancels out this component, right? And all the components of these vectors along the z axis add up, no? Hence, making our calculation, what do you call this? it makes our calculation easier, no? Because we already argued symmetry, no? There's a symmetry that can be applied to this problem, no? And that is the reason why we are only interested with what dBz is, no? So dBz is given by mu naught over 4 pi IDL sine phi over r squared multiplied by sine theta. Now you might be wondering why we have this term sine theta. That's the next thing that I want to look at. No? It's really very hard to um, use this platform. I'm actually using PowerPoint for this lecture, no? But maybe we can weather through this, I hope. Okay, so we are already able we were able sorry we were able to justify why we are only interested with the z component of the infinitesimal magnetic field. Again, if you consider pairs, no, so for example this one and this one, that's one pair, no, their components along this direction will just cancel out. And if you consider another pair here, you will see with the same analysis that the components also cancel out with each other. No? Um, now, if we define uh, dB to be some vector, sorry, if we define dB to be some infinitesimal vector that is oriented by some angle theta, no, from an axis, say this is from the y-axis, no, we can decompose, no, your dB into its z and y components. No? Now we can imagine this to be a right triangle, no, which we can draw like this. So this is your right triangle, this is your dB, this is your dby, and this is your dbz. Okay, now since we defined theta here to be this angle, no, we can say that dBz is just equal to dB sine theta. Since sine theta is defined as your what do you call this, opposite over hypotenuse. In the same way, we can also write down dby in terms of this theta. So this is just equal to sorry, that's just equal to dB cosine theta. Okay, and that's the reason why we were able to write dBz in terms of this angle theta. No, now what is left for us to identify is what r is. No, r is just it's simply this length, no, which can be obtained using your Pythagorean theorem. No, so of course to obtain the infinite or the net magnetic field at point P due to this circular loop, what we need to do is to integrate this, no, over this whole circular loop. Okay, so that's the next step that we have to do. But of course, we first have to know what sine theta is, right? Because sine theta in this case, it can be defined in terms of what do you call this? In terms of known quantities. What do I mean by known quantities? We really do not know what theta is in this case. We just defined theta to be this angle. However, we are only given with the radius. So this is the radius and the distance, no, of point P from the origin, which we can write as z. No? Therefore, we must be able to express your sine theta in terms of r and z. And that we can do by using your trigonometric relations. No? Now, since we define this to be theta, we know that this angle is the complementary of theta, which is pi over 2 minus theta. Now, by inspection, we can already see that this angle, which is complementary to this angle, is just theta. No? So the angle between DB and the y-axis and this angle are the same. No? So we can readily express sine theta in terms of r and z. And that is given by this, r over square root of z squared plus r squared. No? Because r is your opposite side. And square root of z squared plus r squared is the length of the hypotenuse of your right triangle. No? This gives us an expression for dBz that is equal to mu naught over 4 pi IR dl over the square root of z squared plus r squared raised to 3/2. Now, here, in this case, the integration variable is dl. We are integrating about the whole length of your loop. Okay? So if we do that, what we get is this term multiplied by 2 pi r. No? Why is it 2 pi r? Integrating your infinitesimal arc length is just actually equal to adding up all the small pieces of your circle, no? And ending up with the whole circle, which gives us this perimeter, which is 2 pi r. No? If we multiply that 2 pi r with your mu naught over 4 pi IR over z squared plus r squared raised to 3/2, no? What you get is this magnitude for the circular loop, which is just mu naught I over 2 r squared over z squared plus r squared raised to 3/2. And that is the magnetic field at some point P that is located a z distance from the origin. No? Now, of course, we can look at the what do you call it? The magnetic field at the center of the loop. No, you might you might guess that the magnetic field at the center of the loop is just equal to 0. No? However, we can see here clearly that it is only it's a quantity dependent on the radius of the loop. No? And it is equal to mu naught I over 2r. And it's not 0. No? It's not 0 because obviously the magnetic field due to each dl is pointing in this way. No? So for example, this one, we can actually make an illustration. So if this is your loop, no? And if you consider a point here that is at the center of the loop, no? We can define dl to be some vector that is defined as a tangent to the circular loop. Here is your r hat, and that is pointing towards, so this is your r hat, is pointing towards the center. This is your dl. If you do your dl cross r hat, somewhere here, the field is actually pointing upwards. No? And if you do that for several other DLs along this loop, what you get is a net upward circular, what do you call it? A net upward magnetic field, no? Which actually leads us to this convention, no? We can actually what do you call this? We can actually get the direction of the magnetic field due to a circular loop by doing your right hand rule as well, no? If you have a circular loop, what you can do is use your right hand, no? Curl your hand towards the direction of the current, no? And whatever the direction of your thumb is signifies the direction of the magnetic field, no? So if it is um, for example, it's counterclockwise for me, so ito counterclockwise pataas, kung clockwise pababa, no? So that's the subtle difference, no? So you can also use your right hand rule. Of course, the calculation involves cross products. So it's very natural that we can always use the right hand rule in obtaining the direction of the magnetic field. Okay, so here are some remarks. Remember that there is a z dependence, no? That is, if we go out along the axis, the magnitude of the magnetic field decreases, no? So kung yan, meron kang loop, so meron kang loop na ganyan, no? If you move along, I mean, if you move away, no, from the loop along its axis, no, the magnetic field at that point actually decreases, no? And you will achieve the maximum value of the magnetic field if z is equal to 0, no? Now, this derived formula is valid only when solving magnetic fields at the rotational symmetry axis, no? Like a cylinder, no? So parang cylindrical yung symmetry. That's what we refer to as a rotational symmetry axis. Okay. So in summary, this is your magnetic field due to a circular loop along. No? This is along the axis, no, of the circular loop. Of course, if you consider a point somewhere here, no, syempre, iba na yung magnetic field dyan. No? It will be drastically different. Very different. So if you do your calculation, of course, iba-iba na rin yung DL, iba-iba na rin yung R hat for this case. For iba na siya from this case. Okay? So yeah. This only works, this analysis only works because of the what do you call this? Rotational symmetry, no? Kapag ni-rotate kapag na-consider tayo ng DLs along this circular loop, para nag-rotate lang tong DB, forming a cone, no? Kaya nagka-cancel out lang yung nagka-cancel out lang yung mga ganitong components, and whatever is left in the DB is this, no? Which is along the z-axis. Okay. So in this case, if we want to compute for the magnetic field due to a circular loop with n turns, we just have to multiply by n, no? Because since we can actually look at a circular loop with n turns as n circular loops that are superposed to each other, no? You might confuse this with a solenoid, no? They are fairly different things because a solenoid is a circular loop of n turns with length L, no? Whereas this circular loop with n turns that we are referring to are actually this is what do you call this? A circular loop with the same radius that is turned combined, no, to form, well, what do you call this? Another loop, no, that has n turns. So it's different. It's fairly different from a solenoid, no, which you will see later on. No? We will use that example for Ampere's law. Excuse me. Now, of course, we can generalize this. Ay, yun nga, as I have said earlier, we just have to multiply the previous expression that we have obtained by n, no? Therefore giving us the effective magnetic field, Bz, no? And at the center of the circular loop of n turns, z is just equal to 0, therefore leaving us with this expression, which is equal to mu naught Ni over 2r. So that's just a simple generalization, no? Now, um, in this can actually be written in a more general manner, no? Because this is, of course, this expression is not only applicable for circular loops, no? We can actually write the magnetic field due to a current carrying loop, no? With a magnetic dipole moment mu. So remember that we have defined earlier what um, the magnetic dipole moment is. No, the magnetic dipole moment is just given by your I multiplied by a, where the magnet or well the magnitude is I times a, but the direction is given by your right hand rule. Okay, so the way for us, no, to obtain this general form for different loops, no, is by actually uh, writing this down in terms of this form. So there is an Ni pi r squared. No? You can just multiply the numerator and the denominator by pi. This turns into your mu, therefore giving you this form, which is mu naught mu over 2 pi r squared plus z squared raised to 3 halves. So this is just some sort of generalization for current loops. Okay. Now, of course, we are not only interested with the expression for a for the magnetic field in a bent wire. I don't know, a circular loop. No, there are also cases when we have to identify the magnetic field due to a bent wire, which you will see later on. No, what we did a while back is just for circular loops. It's a closed loop. No, there are symmetry arguments. However, there might be questions that look like this. No, what is the magnetic field due to this current carrying wire? No, so kita nyo, you have a straight segment, no, and a circular segment which is not actually closed. No, so we must be able to obtain the magnetic field due to a bent wire with an angle phi, where phi is this angle that subtends this length. No? So that's how we define this angle phi. Now we ask, what is the magnetic field at point C at the origin? Now, of course, in this illustration, we are they call this we are looking at C at some as some center of curvature, no? Therefore it means that if we extend this, no, try to close this with the same radius r, we will form a circle, and the center of that circle is still C. Okay, so that's what we mean by the center of curvature. No? Now, how do we obtain? So we can define an R hat and a DL, no, for this system. No? So for example, for a current carrying element somewhere here, no, DL, if the current is flowing in this direction, no, as shown, no, DL is this vector, while R hat is the vector that is unit vector that is pointing from the source point down to the field point. So this is your, again, your field point. This is your source point. No? Now, dB, or the magnitude of the magnetic field, is just given by IDL sine phi. However, we can already see that anywhere along this loop, this angle between DL and R hat is just equal to 90 degrees. They're always perpendicular. Hence, this sine phi is just equal to 1. No? Also, in this case, since we assumed C to be the center of curvature of this arc length, no, we defined the R here, the distance between the source point and the field point, to be your capital R, which is the radius of curvature. No? And lastly, we can actually perform the integration. No? Since we already identify what sine phi is, what R is, what I is, no, we are left with an integration of dl, no, where dl is of course some R times phi, no. Now the reason why we got this is because dl in this case is just equal to R multiplied by d theta. Now remember that the arc length L that is subtended by an angle theta with radius R is just theta R. And if you get the infinitesimal dl, that is just equal to capital R multiplied by d theta. No? If you get to integrate that from 0 to phi, where phi is this opening angle, or this subtended angle, no? What you get is an expression equal to mu naught I phi over 4 pi r. So this is the magnitude of the what do you call this? The magnetic field due to a bent wire. No? You can see actually that this expression gives the same magnitude as that of the circular loop when phi is equal to 2 pi, that is, this bent wire is a full circle, no? This becomes mu naught I over 2r, no? Which is the result that we obtained earlier. No? So that's the what do you call this? That's the magnitude. Now, of course, to obtain the direction, no, you just have to use your right hand rule. No? So, kung paganyan yung direction ng current, ibig sabihin nun, yung magnetic field ay paganyan. No? If pababa naman, edi yung magnetic field paganyan. So, you can just use your right hand rule for this case. Okay? So, yan na naman yung illustrations. So, let us consider an example. Let us consider a circular conducting loop with radius 10 centimeters. So, this is your R. Lying in the YZ plane, centered at the origin. It carries a current I equal to 1.5, and it is directed counterclockwise as viewed from the positive x-axis. So you can imagine this as this one. No? So if we do a 2D analysis of this, if you have here the y-axis, no, and the positive x-axis is pointing out of the page, no? Z is pointing here, right? that right? Yeah, yeah, tama. This is your x, this is your z, this is your y. No, we are asked what is the magnitude of the magnetic field at the origin. We can easily see the direction of the magnetic field for this case. No, we just have to do your what do you call this? Your right hand rule. No, your current is flowing in this direction. No, so paganyan siya. Therefore, what do you call this? The direction of the magnetic field is actually in the positive x hat direction. No? Regarding the magnitude, we just have to use your what do you call this? Uh, expression. It's just mu naught I over 2r, right? That's what we got earlier. So doing your mu naught I over 2r, what you get is that. No. Now, this is the one that I illustrated before. We want to find the magnitude and direction of the magnetic field at point P due to the current in the semicircular section of wire. No? Um, uh, we want to get no, all this, no, all the contributions of these currents. No? But before we start the calculation, you can already see that some of the segments will not contribute. No? So in this case, you have here, if you consider a DL somewhere here, it is pointed in this direction. No? Our hat is pointing from the source point to the field point. Therefore, it's in the same direction as your I hat. Therefore, this will not contribute to the magnetic field at point P. No? On the other hand, DL for this part of the segment is pointing in that direction, while DR is pointing in the opposite direction. Actually, it's in the anti-parallel direction. Therefore, this segment also does not contribute to the magnetic field. So we are only interested with the contribution of this segment, which is in which the current is flowing clockwise from this perspective. Okay, so the magnetic field from the origin uh, is just given by 1/2 mu naught I over 2r. No? Why is it 1/2? Because mu naught I over 2r is the contribution of a whole circle. No? If we divide that by 2, what we get is the contribution of the semicircle. No? Since parang ano lang yan, if we have a whole circle, no, we want to add a contribution, right? If we consider only a semicircle, kalahati lang nun yung ina-add natin through the summation, no? And the rest are neglected. So that's why we multiplied mu naught I over 2r by 1/2. Okay. On the other hand, we can also use the formula that we have obtained earlier, no, from the bent wire formulation, no, mu naught I phi over 4 pi r. No? Since this is a semicircular loop, no, this is a bent wire of angle theta, angle pi, which is 180 degrees, we get the same result, which is mu naught I over 4r. Now, if you want to get a direction, no, since your current is flowing in the clockwise direction, no, so you can what do you call this? Curl your hand towards the direction of your current, and the your thumb will point towards the direction of your magnetic field. No? So again, the straight sections have no contribution because DL and R hat are either parallel or anti-parallel for both segments. Okay. Okay. let's consider another exercise. So we have here an exercise in which we will consider a current loop that looks like this. No? So here you have a current that is flowing this direction, then a counterclockwise direction flowing current, then downward, then a clockwise moving current. No, so it is always important that you have to visualize the flow of the current for this case. No, kasi again, kunyari in this case, your I is flowing in the counterclockwise direction for radius B. Tapos, dito sa A, it's flowing in the clockwise direction. So, of course, the magnetic field contributions for each circular segment will be the same. Will not be the same. No? Um, I guess uh, it is proper that we consider that first. No? So, if you do your right hand rule for radius A, so this is your radius A. No? Nag-move clockwise yung current. This is your current A. No? Current A, if you do your right hand rule, so papaganon siya, it means that the magnetic field due to A is pointing in the negative Z direction. So this is negative K hat. No? While if we consider B, which is pointing in this direction. So, kapag ginawa niyo yung right hand rule, pag ganyan, mag-curl pa ganito. And, actually, this current will contribute a magnetic field that is pointing out of the page. No? So, into the page, out of the page. Hence, whatever the contribution is of um, segment A should be negative, and whatever the contribution is of segment B should be positive. No? So we can already cross out two components. No? This one and this one. No? Because here A is positive and B is negative. Now, there's also another one that we can cross out. No, we are already sure that the magnetic field is not zero. No, at the origin. The reason why that is because for a circle, a bent wire, it's given by mu naught I phi over 2 r. No, 2 pi r. Sorry, 2 pi r. Ay, 4 pi r, sorry, 4 pi r. There, it's 4 pi r. Okay. Now, since we already know that it's mu naught I over 4 pi r, there is an explicit dependence on the radius of the bent wire. No? And of course, we can already see, no? Wala namang masyadong mahiwaga dyan. A is smaller than B. Therefore, the contribution will not be equal to 0. They are not equal. So, this can also be crossed out. The only deciding factor is whether it is a factor of 1/2 or a factor of 1/8. No? How do we determine that? No? We identify phi to be equal to pi over 2. No? Because this is a quarter circle. No? And if you apply your pi over 2 to this problem, what you get as an answer is letter E. So the answer for this item is letter E. Okay. So this is purely analytic. It just depends on how you analyze the problem. Huh? Medyo mahirap lang. The complication arises from the analysis on whether the direction is out of the page, into the page, which actually it heavily relies on your understanding of the right hand rule. Okay, so yeah, so again, the answer is mu naught I over 8r. Okay, so we are done actually with the application of Biot-Savart law to um, systems, no? Different systems involving different geometries. No? So we had straight line geometry, and we had your curved geometry. No? The next lesson that we will have on Ampere's law, no? Which will be covered in the next video. No? Ampere's law is um, technically, well, not technically, but an analog of Gauss's law in electricity. No, Sibasa, to get the electric field, no, we said that the electric field is proportional to the amount of charge enclosed by a surface. No, here we will see that in Ampere's law, the amount or the magnitude of the magnetic field is proportional, no, to the amount of current that is enclosed by a closed path. No? So sa Gauss's law, you have a closed surface. On the other hand, what do you call it? Sa Ampere's law, you have closed paths. No? So we will apply Ampere's law um, for different configurations in the next lecture. Okay? Thank you very much.